if people settle in again. Alright, thank you so much for the introduction and thank you so much for having me. This is, I believe this is the first time I've been to the Department of Mathematics here in North Campus, even though I'm a Delhi University, very proud Delhi University product. So it is absolutely wonderful to be here for the first time and definitely very wonderful to be speaking to all of you. And now I think this is possibly the largest group of people I've spoken to. So I will be talking about Markov chain Monte Carlo, and I'm going to try to introduce it in a somewhat gentle way. Professor Dootika was very kind to help sort of explain to me what might be your prerequisite background, but if you don't mind, I will do a short poll. How many of us have had a somewhat introductory course in probability? It's okay if you don't remember anything, but have you had a course in probability? Okay, well that's very promising. And how many of us have had courses in statistics? Okay, excellent. That's also very promising. The rest of you, I will also be speaking to you, don't worry about it. But just for me to understand how many people know a little bit of that. Okay, so Markov chain Monte Carlo is a research area of mine. And so what I'll try to do is slowly explain what the area is. I will possibly not do a very good job of motivating why this is a research area. And the reason is it's somewhat a little bit of a probability and statistics background that's deeper is maybe important to actually understand what is the need of the area. I'll try my level best, but if you have questions like that, I'm happy to talk to you afterwards as well. Okay, so what is this area? So the first thing to sort of remember is how many of you have seen the movie Oppenheimer? Okay. Do you remember the slight villainous character in that film? Slight villainous. One, yeah, not the actor, but the character. So anyone remember Edward Teller? Sorry. Slight villainous, somebody who, yeah, okay, very nice. So I'm not sure if how much truth there is, but one of the people involved in really defining Markov chain Monte Carlo was the physicist Ed Teller, along with folks like Metropolis Hastings and Rosenbluth. And the first use of Markov chain Monte Carlo as an area was in World War II in cracking codes, war codes. So there is some application that this area has, certainly because the invention of this whole field was because of a certain application that was required in World War II. So it was first developed and used by physicists. A lot of the details to study Markov chain Monte Carlo are grounded in probability theory. So even though I call myself a card-carrying statistician, I still have to somewhat be fairly sound in my probability theory background. The algorithm as we know it today is often developed by statisticians like me. However, when we actually develop something, we go and read the physics literature and we find that somebody in physics already did a version of it, which is always a little bit disappointing. So the physics people are very, very creative in coming up with new algorithms like this. But the main thing is that this whole space of Markov chain Monte Carlo algorithms, whatever it is used very, very often outside of math and statistics. So it's used by statisticians, but computer scientists, biologists, economists, neurologists, astronomers, and also now in large language models. So we'll sort of understand what is it actually doing. What does it do? It replaces integration. Basically, it replaces integration. That's the one word summary of Markov chain Monte Carlo, that you don't now need, because of this method, you don't need to evaluate integration if you are. So let's understand that. Okay. How many of us are familiar with integration? Very good. So everyone's awake. Very nice. Great. So let's say I have an expression like this, integral of f of x dx. We'll do a little bit of brain-warming exercises. Do we know the answer of integral x dx from 0 to 1? Yes, I heard everyone at the same time. 1 by 2. 1 by 2. Okay, very nice. That is indeed 1 by 2. What about this? It's slightly more complicated. Like double integrals. But these integrals are nice and separable. Right? So what do we get? It's 1 by 3 times 1 by 3. So that becomes 1 by 9. Very nice. What about this integral? अब रुकेंगे, अब थमेंगे सब लोग, थोड़ा सोचेंगे. Not as easy. You have to maybe work it out if you've done it before. Maybe you know. You can sort of do it, right? You know that there's a path to do it, right? Okay, you get something I didn't do. But by my virtue of being a statistician, now I'm lazy about mathematical integrals, so I don't actually solve them. Okay? Okay, but you know there's a path to it, and you can solve this. Now, a lot of integrals that you've seen so far are given to you because they're solvable. Right? They're in your 12th class textbooks, in your maybe your undergraduate, maybe you might come across them in your masters. These are nice, well-behaved integrals, and they are given to you and taught to you, and you're faced with them because they are solvable. Right? So there is what we call a bias there, because if it was not solvable, it wouldn't be actually given to you as a problem, right? But there are also integrals like this. It's a 100-dimensional integral. You have x1 times x2 times e to the power x1 cube, sine of x1 squared, and then there's 98 other variables, and you have to integrate over all of these things, assuming whatever this function is indeed integrable. Right? And that you can imagine is now very difficult, right? Correct? I mean, I was so lazy, I want to even write out the whole integral. So how do we then go about calculating these integrals when we don't actually know their analytical closed form answers? So this is really the motivation of this whole field of Markov chain Monte Carlo. It replaces integration. And if you learn nothing else today, you should learn the following: that you don't want to be a mathematician when it comes to integrals. I apologize to the professors here. When it comes to integrals, let's put it on me, you do whatever you want. I don't want to be a mathematician. Okay, because I'm faced with integrals like that all the time, and if I try to evaluate it, umar beat jayegi. Okay, so what can we do instead? Well, we solve this problem using probability or statistics and some sort of error. So the first question I want to ask you is, what is the difference between math and statistics? The answer is up here, but before really reading it, can somebody tell me a difference between mathematics and statistics? This is not a you are correct, you are wrong answer question, right? It's a personal opinion of yours. Somebody brave enough to voice their personal opinion. Yes, please, sir. Yes, please. My question was not what's the difference between mathematicians and statisticians. Right.
Okay, statistics is a branch of what?
Studying data.
So, and what is that branch? What that data, whatever you are talking, that process is a part of what? Come on, I want to hear something from you, It's a process of what? I'm sorry to have got
No, please go ahead.
Approximation, linear regression.
Yeah, all that is what?
Okay, thank you very much. What's your name, please? Anurag. Thank you, Anurag. Okay, so this can become a very heated argument. I shouldn't have put this, but actually I would slightly disagree with this concept that statistics is a field of mathematics, and it's only a philosophical disagreement. For me, statistics is as much a field of mathematics as theoretical physics. We require high-intensity mathematics all the time, just like theoretical physicists. But philosophically, there's a difference in the kind of problems statisticians typically think about. Okay? And if you are able to attend the talk in the afternoon, you might see a little bit of hint of that. I'm not going to go over that debate today, and this morning at least. But for the purpose of integral evaluation, as a mathematician, I would like a deterministic answer कि ये integral है, ये क्या है? Right? What is this integral? Right? I want an exact value of the integral, and because it's an exact value, there is no room for error. Error cannot enter the chapter. But as a statistician, my answer on the integral will be a probabilistic answer, which means that आज I will give you one number, tomorrow I might give you another number of the integral. Okay? There is going to be some method to the chaos. ऐसा नहीं कि अपने mood से I will give you a number. Right? There will be some sort of a method to that calculation. I will approximate the integral. I will not exactly tell you what that integral is. I'll give you an approximate answer, but by virtue of being a statistician, my job is to tell you some amount of uncertainty and error in my approximation, not the exact error. If I knew the exact error, I could tell you the exact answer. Right? But I'll give you some sort of an assessment of how much error there might be. And that is what a statistical answer for evaluating an integral might be. So let's think about how we could possibly do this. So the method we will use is Monte Carlo integration. How many of you have heard about Monte Carlo integration, Monte Carlo estimation? Finance people sometimes, maybe portfolio optimization. Okay, some of this. Okay, so let's try and do an exercise. Again, a simple integral to warm up your brains. What is this integral? 1 by 3, right? Integral 0 to 1, x squared is 1 by 3. We know this. Because we know this, we know we can try to also see how we might go about estimating or approximating. Okay? So this is the plot of my function f of x from 0 to 1. Okay? This is what x squared looks like, and I want to integrate it. Now, an integral is nothing but the blank under the blank. Area under the curve, right? That's what an integral is, at least integrals of this form, right? So what I want to know is what is the area under this curve. And as an answer that is not an exact answer, I can try to do using ideas which you might be familiar with from Riemann integration. Okay? But I'll do it slightly differently. What I'm going to do is I'm going to generate a random number. A random number means किसी तरह एक कंप्यूटर ने एक नंबर उजाड़ किया, just gave me a number between 0 and 1. Okay, I had no control over what should that number be. It gave me a number randomly between 0 and 1. Let's say it was about this number. What I'll do then is I will go up and I will obtain the function value at that number, and then me being a lazy person, I will just say if this was a rectangle, I assume that the function is a rectangle, right? And I'm just going to say, well, this is my guess of the area. Right? So if the function was a rectangle and I know the space is between 0 and 1, the height of the function is then going to give me the area of my function. So what I'm imagining is I don't really know what this whole function is. I just have access to its value at one point. That's it. Okay? And then I say, okay, this is my guess. Right? Is this a good guess? Hopefully, one thing we can all agree on is that this is not a good guess. So, very good. So what could we do next? Well, we could get another point. If a computer can give us one number, it can give us many numbers. Right? So I'll take another number randomly, again random, not on a grid, and it got this number. When to estimate the function at this value, and then basically assume that each of the rectangles is half the base of the other rectangle, half of the base of the previous rectangle. What I mean by that is I get something like this. Right? So I basically reduce the base by half, and I reduce the base by half here, and I take the sum of those. Right? Of these rectangles, and this is the current area, estimate of my area, approximation of my area. Is this a good estimate? No. Okay, again we can agree on that. Okay, well we can do this again. I can do this now with 10 points, right? There's nothing stopping me from doing it with more points, right? So I just do this with 10 points. And now each of the width of this rectangles will be 1 by 10 of the original width. And I make rectangles of that size. And now, you know, what happens is at some point, obviously, I have a little higher area, and some points I have a little lower area. And I'm hoping some of that will cancel out. And now my approximation of the area is 0.39. Right? And I could now now do this with 100 points, and when I do this with 100 randomly chosen points, I'm not putting points in a grid, which is what typically you would do in a Riemann integration. I'm just randomly putting points on the x-axis, and now this starts looking very much like my exact integral. At this point, it is exactly 0.33, but I've rounded it off. There's a little bit more noise there. Okay? But you can see this is not exactly accurate, right? Because there are pockets I've missed and pockets where I have an overlap of rectangles. But that's okay. Okay, as long as the idea that behind this experiment is that if I put enough of these, enough crowd here on my 0 to 1, I will be able to get a reasonable approximation of the integral. Okay, this is by picture. Let's do this by map. So what do we get? Well, here's what we're doing. What we're doing is we're getting x1, x2, xn, and these are uniformly and randomly distributed on 0, 1. Randomly distributed, you understand, where it's just basically a computer can randomly give you a number between 0 and 1. Uniformly means that no number between 0 and 1 is more likely than any other number. Right? All numbers are equally likely to appear. Okay? So there's no bias that I favor one number near 1 more, number near 0. Okay? So there for each of these xi, what's happening is that for each xi, I'm going to calculate the height of the function at that xi, so that's f of xi, and then I'm going to create a box of base 1. Right? That's what we did in our first class. Right? A box of base 1, which is my integral limits were 0 to 1, and the height was f of xi, and then the area of the box is f of xi times 1. That's my area of my rectangle, and then I can do this with all of these xi's. Right? Why waste the other xi's? I can use all of the xi's. So what I get is the average of the area of the boxes, integral f of x dx, is approximately the average of all of the areas. Right? And I can actually, what I can do is I can write it slightly differently, which will match my actual image that I take. I can distribute this n to each of the fx's, and when I do this, another way to think about it is I take an area with base 1 by n, right? And I add all of those rectangles, which is exactly what I did in the previous image. Okay? And so now I have an estimate of an integral using these values. I'm sorry if somebody can't read this at the bottom, but I have integral from 0 to 1 x squared dx is approximately the average of each of the xi squares, because that's the function value, xi squares. Okay? Can somebody now try and tell me what is now the difference between estimation and approximation? At least some of these are not definitions, these are personal opinions, but I'm trying to move you in that direction. Okay? So what do you think is what I mean by estimation, and what do I mean by approximation? This is a class, right? As far as I understand, we're in a classroom, right? With some guests that we've invited, and we're in the classroom. Yes, please. What's your name? Ritik, yes, please go ahead. There's going to be an error here also, right? The error over here is also, this is not going to be an exact point 1 by 3. Okay, you're close enough, but you're missing a key insight. Thank you, Ritik. The key insight at least is that an approximation, Riemann integration also gives you an approximation to the integral, right? But that is a deterministic approximation. Means that if you repeat it every time, you're not going to get a different answer. Right? You're going to get the same answer repeating that same algorithm. The key difference here is that these numbers were obtained randomly between the interval 0 and 1, which means every time I do this, I'm going to get a different answer. But I will rely on some certain characteristics and certain rules of mathematics that tell me that if I get enough grid points, enough draws, enough samples between 0 and 1, I will still be able to get a reasonable guess no matter when I run this whole experiment again. Right? And that's coming from this philosophy of the result of law of large numbers. Do we know law of large numbers? Right? Or law of averages? Yeah, it's similar to law of averages. Right? It basically now tells me as the number of data increase, my x's on the grid are my data. As they increase, their average will converge to the true integral. Okay? So what I do now is this is the number of points, and this is my estimate of the integral as my number of points increase. So जैसे मेरे rectangles are, I am updating my estimate of the integral, and I can see that in the beginning the answer, the guess is really bad, right? That I have very low number of rectangles, very low number of grid points. But eventually, once I get, let's say, 10,000 points, I am exceptionally close to the truth that's indicated in this horizontal. So there is a method to the madness. So the mathematics of these objects, these averages, helps us rest easy that if I do this long enough, I'm still going to get some stable guesses. Right? Very good. We move on to another example, just to motivate how we think about integrals, how we think about sampling as well. So what we've done so far is we've just done averages of points obtained randomly between 0 and 1. But I can also be faced with problems where I need to get these samples, these draws, these x's from a different place. Right? I may want to draw values from all real lines. I may want to draw values from within a circle, for example. And so what we are going to do is now try to estimate the area of a circle using similar ideas, and we'll build up to Markov chain Monte Carlo. Okay. So what I'm going to look at is a circle that's centered at the origin, and it has radius 1. So it sort of looks something like this, and I want to try find the area of a circle. This is also a very common experiment that we do in sometimes in undergraduate. I remembered at one point I did this during my degree math. Anybody has done this before? All right. So what I'm going to do is what I want to do is be able to somehow obtain the area of this using some random process, right? Not just not just take out a scale and then measure and use the formula pi r squared. I don't know such a formula maybe exists. So here's what I'm going to do is I'm going to take my circle and I'm going to perfectly enclose it in a box, in a square. Right? Now what I'm going to do is I'm going to draw random points on the square. I can draw random points on the square because I know how to draw random points on each axis. On each axis from -1 to 1 I can draw any point. From -1 to 1 on the y-axis I can draw a point. I take that point here, and that's a point in my box. Right? The tuple becomes a point in my box. So I can draw random points inside the box. And now what I'm going to do for each point that I draw, like this point, I'm going to check if its coordinates satisfy being less than 1 or greater than 1, because that's my equation of a circle. Right? If they satisfy being less than 1, then they're inside the circle, and I'll color them by blue. And if they are outside the circle, right, that means they're in the square but outside the circle, I'll color them by red. And this one is inside the circle. That little one there, if you can't see, that one's outside the circle. It's always going to be in the box because I'm actually drawing random points from the box. Right? This one's again inside the circle, and I keep doing this and I get these random points floated everywhere, inside and outside. We'll keep going on for a while, and what I'll end up doing is I'll get a bunch of these red points outside the circle, which I ignored. I don't use those circle mein haenge. Okay? And I use only the ones that are inside the circle. Those are my blue points. Somehow I need to use this to estimate the area of the circle. What I can use is the fact that I know the area of the square. Right? If I know the area of the, what's the area of this square? Hypothetical chocolate to those who get it. Yeah? Yum, 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 yum. This is all I hear. कोई एक हाथ उठाइए भाई, somebody blame me so I can. No, not really. Yes, ma'am. 4. Very good. So the area of the square is 4. We know this much. Very good. And the way then to estimate the area of the circle is to say, well, how many are inside the circle, right? Because that's the cutout that makes the circle. And that's exactly what we do. The area of the circle is the proportion of points that are in the circle times the area of the square. And so what I do is I randomly sample this tuple x1, x2, 1, x1, x2, n from the square. These tuples I get from the square, and then I check what proportion of points are inside the circle, multiply by the square, that gives me an estimate of the circle. Right? And so in this particular case, so how do I do this? Well, mathematically I can create a new object zi, which is the indicator function that this tuple x1, x2, I is in the circle. We know indicator functions, right? They're 1 or 0, right? So this is now going to be 1 if the point is in the circle and 0 otherwise. And the key is I can check this condition, right? Because I know the equation of a circle. I can check this condition and get for each point a 1 or a 0. And there's a proportion of points on the circle. Note is now nothing but an average. Because all the ones that are 0 become 0. Again, so we come back to an average, right? So this now is an average. I multiply this average by 4. And in this case, area of circle becomes 4 by times this p hat. Okay? And again, I can run this. Again, it will give me a law of large numbers. I run this again as I increase points keep drawing points from my square. And in the beginning, I get a really bad estimate of the area of my circle. And then eventually, I try to stabilize at pi, because pi is the area of the circle, right? Pi r square. Correct? Is okay? Very good. None of this has anything to do with Markov chain. Because I said my area that I want to talk about is Markov chain Monte Carlo. Correct? So what does this have to do with Markov chain? So now let me ask you, how many of you know what a Markov chain is? Even if you don't remember. If you've had a course in it. Okay, very good. So let's try and get ourselves a little familiar with it. I'm not going to use a lot of mathematical notation, but I'm going to motivate by extending the same example. I know I have a circle. Now what if that circle was a sphere in some d dimension? So now we're coming into your territory of abstractness, right? I can't really imagine this d-dimensional sphere, but I know it exists, right? What is the volume of the sphere? I want to estimate the volume of a d-sphere. Okay? And that is the integral over the fact that the norm of x is less than 1. It should be equal to norm squared x is less than 1 dx, right? Because what is the norm? This is Euclidean norm. So the norm squared is x1 squared plus x2 squared plus x3 squared less than equal to 1. That's my integral area, right? So the way to do this now is very similar. If I have a sphere now, what I'll do is I'll enclose it in a cuboid, in a d cube or a d-dimensional cuboid, right? And in a d dimensions, I'll do the same. Correct? And I'll use the same exact formula and the same exact understanding that the volume of the sphere is going to be points in the sphere divided by points in the cuboid. So the proportion of points that are actually in my sphere times the volume of the cuboid, which I know is 2 to the power 3. Right? Correct? Similarly, I can do this, right? Everybody agrees we can do this? Okay. This is the difference now between theoretically doing something and practically doing something. We can do this theoretically, but there is a practical problem. Here's the practical problem. That this proportion T, this thing over here, can be small when D is large. And this is, if you've heard of the phrase cursive dimensionality, this is an indication of cursive dimensionality. So to give you an idea, when D is 2, and here by D equals 2, I mean a sphere in a square. When D is 2, my proportion is 78%. So 78% of the times I will lie inside my circle, 22% of the times I will lie outside my circle. Okay? Very simple. When D is 10, proportion is 0.0025. That's quite small, right? Okay, now let's say you're in an example in an application where D is 50 dimensional. Can we guess what T would be? Very quickly, can 2 people tell me their guesses for T? Extrapolate if you want to. give me any number that's a valid probability. Chalega. Sorry, say that again. Who's this? 10 to the power Anurag, right? 10 to the power minus 10. That's 1. Is that seems very, very small, but maybe that's okay. Anyone else? अरे कुछ भी बोल दो. आगे बढ़ना है मुझे. 10 to the power minus 100. Okay. Well, that's going to be very, very small. But actually, this is not outside the realm of reality. It's 10 to the power minus 28. And actually, if you take d equals about 55, we get to about 10 to the power minus 100. Okay? Now, ये सब theory में तो ठीक है, but इसका क्या impact क्या है? What is the impact of this? Well, the impact of this probability is that to get one draw from inside the sphere, you will have to throw 10 to the power 28 draws from inside the cuboid. Right? And this is a massive number. Right? And अभी ये काम आपको 10 लाख बार तो शायद करना पड़े, because you want to get the average, right? And so this is only to get one success. Fair? So this is theoretically possible, but practically not a good way. Okay? This motivates Markov chain Monte Carlo, and this is something that happens nirantar every single time in many applications. As soon as you go to any integration in high dimension, you don't know where the volume of that integral is. If I have one line over here and you need to find an integral under the curve of that one line, you can find out by doing some grid search कि यहाँ पे कहाँ पे माल है, where is the mass. But if I'm in this full room, you need to now do a larger grid search to understand that where is the main area. And the same thing you have to do now in 50 dimensions. You don't know where to look for where the main area is. And that becomes challenging in high dimensions. And the problems we work in are not just in 10, there are thousands and millions of dimensions. Okay? So how can we fix this? One fix is by loosening up on certain criteria, we can potentially do a little better. Okay? In terms of trying to do, not having to do 10 to the power 28 draws. So one of the key reasons of this low efficiency, by efficiency I mean that I have to draw many times from the cuboid to get draws from the sphere. Okay? That's what efficiency means. One of the reasons is कि ये जैसे इसको draw लेना है, it forgets about the previous draw. So for example, I finally found that उस कोने में there is area. And next time I say I will forget that there is the area, I will still search everywhere else. Right? When I know area is in that point. Right? And so this starting the search every single time anew without using any information is going to be not very efficient. Okay? But if I use my current information of where I am right now, that gives me dependence in the next draw and the current draw. Right? So there is something I lose. I don't want dependence because that's not, and you'll see why. Okay. But this is how I will use what is called MCMC, Markov chain Monte Carlo, to now draw. So as long as I know one point in the circle, right? Give me one point in the circle, then I'm good to go. Right? So the center of the circle I know by the equation, so I know the center, or I know something else also. So let's say this is one point on the circle, that's in green. Instead of encapsulating the whole region in a square, I will put a small square around my current point. Okay? And now I will propose the point from here and check, is this inside my circle or not? If it is inside my circle, I'll keep it. If it's outside my circle, I throw it away and stay where I am. Bahar nahi jana hai. Right? I don't refuse to go outside. And so, for example, from this square, I will always only produce points inside the circle because the square is not big enough. And so I propose this and I like it, so I move there. Oops. I like it, I move there. When I move, my square also moves. Right? And then I propose the next point from the circle. And then I like it and I keep moving. So if I keep doing this, I keep moving. And then eventually, you'll see this is going to, the square is going to keep moving. It's gotten all nice circle, nice points so far. Eventually it will go to the corner where it will get some red points. It did not move there, it kept inside. It will keep moving, and then eventually I will fill this whole thing up with some points just on the periphery that I will have had to ignore. In 2 dimensions, it seems similar, but when you're in high dimensions and the mass is only in that one little corner of the room, you're not going to escape that room. Right? You're not going to go and waste resources in the rest of the room. This is a Markov chain Monte Carlo procedure. The Markov chain part comes from the fact that the next draw is conditionally dependent on only my current draw. बोलचाल की भाषा में आगे जाने के लिए बस आज की इंफॉर्मेशन चाहिए, अभी की इंफॉर्मेशन चाहिए, that's it. But then what happens is every new draw is giving me less new information. When I got random samples from everywhere, every new draw was giving you new information. That was completely independent of previous information. But because I've chosen to be dependent on my current draw, every draw is giving me slightly lesser information than if I was allowed to jump everywhere. How do I see this? Well, I see this in the following. I can do the same rule of proportion of points and things like that. And when I do, there's a version of law of large numbers that also holds for these draws as well. Okay, and that's where some of the mathematical and theoretical probability comes in. But when I take what is called the estimate of the area of the circle, I get something like this. Okay. Now I don't as this is up to 10,000 steps, 10,000 draws. After 10,000 draws, I'm not so close to pi, right? Which means that does this not work? Well, it's not true. It's not that it doesn't work. It just takes longer to work. Okay? So I now had to run it. So after about 100,000 or 1 lakh steps, it eventually stabilized around my truth. It's going to always oscillate until it gets to maybe even larger. It stabilized around my truth, and now I get a reasonable number. But at least this was better than trying to get 10 to the power 28 draws from the square to actually get one acceptance inside the sphere. Right? So that's the trade-off. Okay? This is good. Please, can you let me know also how much time I have? I don't know when we eventually start it. Okay. We'll end it. Okay.
What is the probability here? There it was support n equal to d equal to 10. The probability was from 0.0 to 5.
Here it's not the same in this case because so the average probability has increased because of the way. So the average probability now. So first of all, the probability is no longer universal. The probability depends on where I am. Right? If I am at the corner of the circle, right, then the probability of rejection is higher. But if I'm inwards, then the probability of rejection is almost 0. And it also depends on the size of the square that I chose. So it's slightly trickier, and we typically study that by studying Markov transition kernel, which I'll also present. But I'll not be able to go into that math as to how we actually do that. But essentially, this is eventually comes down to an average again, and you track the average as you get more and more samples. In this case, 10,000 observations is not going to be good enough, and so maybe 100,000 is now stable enough to get you to a reasonable estimate of pi. Now, I'm going to go into I'm going to go into slight more mathematical explanation of MCMC. But there are various other applications where such integrals are used. Last year I went to IIT Bombay and I was talking about some other concepts, and there a PhD student told me a wonderful application in computer vision where there are amazing, very complicated integrals. Basically, you have to integrate over all possible light paths to actually view an object, right? So light follows a certain trajectory and all of the paths are coming into my eye. I need to be able to integrate or Monte Carlo techniques there as well. Okay. So let's if we've understood any questions until so far, because we'll go into slightly more mathematical, not very rigorous, but any questions? Yes, sir. So, okay, a good way to think about less information is the fact that I need more samples to get the same information. Right? So every sample is giving me less information, and I can see this by the fact that I need more samples to get back a similar quality of estimation. I mean, if in like statistics and probability, we would say that those samples are independent and identically distributed. These samples are correlated samples, not independent and identically distributed. Okay. So the first thing though, to actually learn about MCMC slightly more completely, is to first understand, well, somehow I have to go from a mathematical problem to a statistical problem, right? And not always will my integral be a bounded integral. So how do I go from a mathematical integral to a statistics problem? Well, I could do the following. I have an integral of f of x dx over r. Now, I cannot get uniformly random numbers on r. And the reason is because r is limitless, and so that distribution does not exist. I can't actually get uniform numbers over r. But what I can do is I can multiply and divide by some function g, right? As long as g is well defined on r. But the g I will choose to multiply and divide by will be a probability density function. It's a PDF. How many of you have heard about the normal distribution? Very good. So think of g as the density of a normal distribution. Okay? So and I'll show you that density as well. Which means that g is positive everywhere and g integrates to 1 on r. As soon as I do this, I'm going to go inside my cupboard and take out my statistician. Okay? Because as soon as I see this integral of something with respect to PDF, I get very excited. Oh, I can do statistics. Okay? This is not very exciting to me. This is very exciting. Okay? I'm a weird person. So, great. The reason this is exciting is now, if you use your first course in probability, you can now view this integral as an expectation. Okay, now I actually know the gap, my statistics gap. Right? I can view this as an expectation. Now an expectation is nothing but an average. I can replace a population expectation, which is this, with a sample expectation using samples, draws from this PDF sheet. Okay, so what do I mean? I will estimate the integral if I can get x1, x2, x3, xn from this distribution G, and I can then, this average, this should be a capital N, this sample average will eventually converge to my population, this integral, when the convergence is in some sense. I chose not to write down the sense of the convergence. Here, the convergence is in some sense. We can no longer think of convergence as just a limit argument because these are random objects. So the convergence is in some sense. Okay, so all I need to do to think of an integral from a statistics point of view is to slap a g over here. This integral becomes an expectation. Once I see an expectation, I can try to get samples from G, take an average, and that average will converge to this. This is very similar to saying if I want to know what is the heights of all Delhi University students, what is the average of the height of all Delhi University students, that's my population. All Delhi University students. Now I can go to every college, every classroom and measure some people's heights. Right? एक दो लोगों की height measure की. I came back and got my x's, x1, x2, x3, xn. Those are my heights of n randomly chosen people. और उनका height का average ले लिया. That will become my population. Guess for my population. Okay? And this same trick is exactly what is used in computer vision, is exactly what's used in various applications in astronomy, in neuroimaging, neural networks, and so on. Okay, so now what's going to happen is once I've done this trick, the name of the game becomes how can I get samples from G? Right? That's the name of the game. Yeah.
Dootika, G, how do you identify G? Right?
Great question. So this becomes a research problem. Yeah. There's a lot of theoretical. So for example, we need some nice properties of this estimator. This estimator must in fact converge, which is often guaranteed, but it must also be what we call a finite variance estimator. That eventually, no matter what n is, its variability from one simulation to the other simulation is not going to be massively large. It must have some reasonable variability that tells me कि हम इसको बहुत देर तक चलाएंगे, then I will eventually get this stability behavior. If it does not have some sort of finite variability from one simulation to the other, then it will keep on going like this, no matter how long you run it, and that's not going to be used. So for that, I need to be able to choose some wise choices. But those are research questions. As long as, yes, so yes to your question, but you might not be guaranteed nice properties. And as long as G integrates to 1 over the support of this integral. So what you need to do is find a G that integrates to 1 is a valid PDF, probability density function over that support, because only then can I write this as an expectation. One my expectation name. Okay. So then the name of the game, like I said, is to get samples from G. These samples are like the same things that we drew from my circle. Circles have samples here, right? Draws here. That's the same idea in a slightly different setup. And G could now, this integral is in R, but it could be in R 1 million. Right? So now I want to draw some samples from some distribution G in a massively high dimension. Yeah.
So this G will depend on every time. Maybe if you change your every time, it will be
So again, good question. So there are certain choices of G that people have come up with that work for a very large family of X. And again, these are all research questions. Okay. Now sampling, though from G, is not very easy. For example, how many of you have coded in Python? Some of you. How many of you know the RAND function, rand function in Python? Okay. Is there a normal distribution ka function in Python also? Something like R-norm or something like that, right? So there is a way to think about it. You need to get a computer to say कि, you have to poke a computer कि, hey, सुनो, मुझे एक random number दो. How does a computer do that? A truly random number, right? That requires certain understanding. Somebody needs to feed into the computer. Look, there is an algorithm that if you run this algorithm, it can repeatedly just keep giving you random numbers. This RAND. Or other, if you've done normal distribution or some other, like maybe like a coin toss, if you do in R, in Python or some other language, if you try to simulate a coin toss, it will come heads and tails with a certain probability. How is it doing randomness? You and I can't do true randomness. All of us have inherent biases. Right? How does a computer do randomness? I'm not going to answer that question, but it's a whole field of study. Right? To get a computer to give you random numbers. If you really think about it, how does one do it? Like, how does a computer do it? It's very difficult. Because a computer is a deterministic process. Everything inside it must run deterministically. So somehow I need to get a computer. ये real life की बात नहीं है. I need to get a computer to give me samples from G. How do we do it? So let's look at a certain example. So for example, this G becomes our target distribution. This is a technical word that I'm targeting this distribution. I want to get samples from G. And the density is small g and it is defined on some space script x. Okay? For example, in my first problem, in the circle problem, x was the disk, right? The circle, inside the circle, script x, and g is the uniform distribution on the disk. Okay, so now I'm relying on some understanding of probability. It's the uniform distribution on the disk, meaning that disk का कोई भी part is not more likely than the other. Right? All parts are equally likely, which means that the density function corresponding to this is going to be g of x1, x2, दो inputs हैं, right, for the x coordinate and the other coordinate, and it must satisfy that integral x square, x1 square plus x2 square has to be less than equal to 1, indicated, and then it must integrate to 1, right? So to get it to integrate to 1, I need to divide by the area, correct? To get it to integrate to 1, I need to divide by the area so that this actually integrates to 1. This becomes the probability density function of a uniform distribution. Uniform कैसे? क्योंकि ये वाला जो part है that has no x1 or x2, right? So the density अगर आप देखिए कि height of the function, height of the distribution क्या है? It's the same on the whole circle. Right? It doesn't depend on x1, x2. Another one which matches the previous slide is when script x is r, so my integral is going from is on the whole r real line, and g is the normal distribution. Let's say normal, mean उसका 0 है, variance 1 है. If you're familiar with the normal distribution. So what does that density function look like? Well, g of x is square root so much. 1 by square root 2 pi e to the power minus x square by 2 is the PDF, probability density function, and this is the shape of the PDF of g. The nothing about this is about f, the actual integral that I want to integrate and integrate. Okay. So now what I want to do is I want to get samples from this g, so I want to get values. Basically I want to sample from this distribution, so I get lots of numbers over here, some smaller numbers, lesser numbers here and lesser number here, and very few numbers beyond this क्योंकि height मान है ही नहीं function. Right? That's what I mean by sampling from a distribution. Right? I want to sample from this distribution, meaning most of my draws will be from here, some of them from here, some of them from here. Okay? And once I do this, then I can go back and take those draws and put it in this, and that will give me an average. So now the rest of this talk is not about the average calculation, it's just about sampling, because that's where the Markov chain comes in. There's many ways to run Markov chains, but what I'll do is I'll just give you a little bit of insight of a very popular algorithm that's called the Metropolis-Hastings algorithm, और यही algorithm हमने circle or square वाले example में चलाया. But let's actually read this algorithm. So algorithm is nothing but a certain couple of sequence of steps that you give to a computer in a way that it can run it, and it just runs those sequence of steps, right? So to run a Markov chain, so what we did in the circle and square example, when the square was moving, I need a starting value, a green dot चाहिए जहाँ से I can actually start, and then I need a mechanism to actually get the next value. Okay? That's it. I need a starting value and a mechanism or a way to obtain the next value. Once I get the next value, right, then that next value becomes the starting value, and the mechanism to update gives me the further next value. And then I can keep doing that, and as I keep doing that, it runs what is called a Markov chain. Okay? And I'm doing a very bad job of explaining the Markov chain. Extremely bad job. But purely intuitive. The way to do this is to then run what is called a Metropolis-Hastings algorithm. Okay, so let's see what this algorithm is. It's one of the simplest, most popular algorithms, and actually there are 4 authors in this. This Metropolis-Hastings, Rosenbluth, and then also Teller from Oppenheimer. I mean Teller from physics, but Teller from Oppenheimer. Okay. So let's say I'm at a green dot, which is my current point, so at some tuple x1 or x2, x1 comma x2, and I want to get my next blue dot or next dot, right? Where do I want to move next in my circle? So the way to do this is I draw y from a proposal distribution. Okay? I will create a proposal that is q xt comma dot. इसका बस ये मतलब है, ये proposal distribution is allowed to depend on the current step. Okay? That's it. इससे हम ड्रॉ करेंगे. Can you guess what was our proposal distribution for the circle example? The smaller square, right? Exactly. The square that kept moving and was then, because it was moving, it was allowed to depend on the current step. Right? And then I have an alpha, which is an acceptance probability. It's a probability which is the minimum of 1 and it's the height of the function PDF at the proposed point divided by the height at the current point. Okay? So so think of, let's say, the normal distribution. If I propose a point that's in an area of higher probability, तो आप वहाँ पक्का जाइए because this ratio is more than 1. Right? If I propose a point that's in an area of low probability, उसको ignore मत करिए क्योंकि I want all points ना eventually. लेकिन उसको थोड़ी कम probability से accept करिए. So alpha is that acceptance probability, and I will set the next point to be this proposed point with this alpha. And if I don't accept it with probability 1 minus alpha, I will stay where I am. हम खुद के लिए, I will pop. Okay, I'll stay where I am. This will define a Markov chain that gets you to the next value. Okay, so let's see. So this is exactly what is happening. In Q, my box is centered at the current state x1, x2. Right? And my alpha is minimum of 1 comma. I gave you the PDF, right, in the previous. So it's just that indicator functions by 1 by pi, लेकिन 1 by pi तो cancel हो गया, right? And so I just get the indicator function. अब यहाँ पे एक amazing चीज़ है that because I'm never moving outside the box, the denominator is always 1. Right? Because I prohibited myself from moving outside the box, right? So is the denominator, is the current value always inside the circle? Yes, it's always inside the circle. And this is either 1 or 0. So the minimum of 1 comma 1 or 0 is just going to be this indicator function. So now all I need to do is propose from the box, check whether the proposed point is inside the circle or outside, and then I move. I move if it's inside, I don't move if it's not inside. And that's it. And that's exactly what this was doing when it was running. So in every step, it basically goes, in every step, this is the current state in the denominator, this is always inside the circle, this is the proposed state in the numerator, this is indicator is always going to be 1 in this case, right? And so it's 1, it accepts, and eventually it will reject. Right? When it rejects, when it rejects, it does not go there, it remains where it is, it hops. Okay? It refuses to go outside. Okay, let's look at example 2, sampling from my normal. This is where you will understand it a little better. So ये थोड़ा सा toy example है. For normal distribution, I don't need an MCMC argument in the top case argument. So my proposal, this is why it's just going to be a normal. Okay, because it's just a toy example, which means I can actually get point draws from this normal. But it's going to be a normal centered at x, और उसका variance 4 है, मतलब थोड़ा सा मोटा normal. Okay. And my alpha probability is minimum of 1 comma e to the constants cancel over e to the power minus y square by 2 by e to the power minus x square by 2. Currently. So if I'm currently here, what it's going to do is it's going to, I hope you can see it in the back, it's going to create a proposal distribution field. ये थोड़ा फैला हुआ है, right? Because its variance is 4. From here it will propose a y, which is this. From this proposed value, you can see that the height at this point is very large. The height of the proposed point is small, so the acceptance probability will be small, right? And so actually this point is rejected, it's in red, and I don't move there, I'll stay where I am. Then I do this again. Same shape of the proposal, लेकिन ये random है, so next time propose draw अलग आएगा. Right? So then I get something like this. Again here also, so it's a random process and I didn't really play with it. तो जो मुझे दिया उसने मैंने चुपचाप ले लिया. It gets rejected. I try this again. Again this will get rejected. It's in an area of low probability. That's fine. Again this will definitely get rejected. That's okay. This now is in an area of high probability. The acceptance probability is more than 1. which means that and the ratio is more than 1, so it definitely accepts. And when it accepts, now if you notice the mean changed to this current ratio. Okay? And then it will keep doing the same thing. And the mean of the proposal will keep on changing based on where I go, and you note that it also goes to the far away points. Because it doesn't reject it, it accepts it with a certain probability. And as I keep doing it, I will get a lot of samples, and what I can do, and this is where, just believe me, make essentially a histogram of all of these samples, okay? And a histogram where I can connect the lines, and that is the blue that tells me roughly ये points जो है वो क्या distribution follow करते हैं, and that starts looking like my underlying truth. Right? Okay, so this algorithm works, at least visually, and how do I know it's drawing from the correct distribution? Well, this is where we need some math. Okay? So what I do is the way a Markov chain ka next step is defined is determined by what is called the Markov chain transition curve. And this is not something you will see very quickly in an intro course to stochastic processes. And the reason is that the space over which I am sampling is a continuous space. It's not a discrete set of points. Okay? It's a continuous space. So how is this transition kernel defined? It's defined in the following way. आप एक पॉइंट लीजिए हमारे स्टेट स्पेस में, हमारे स्पेस में जहाँ से हम शुरू करते हैं, ठीक है? और एक सेट लीजिए, a set in that space, and the kernel is defined as the probability of jumping to a set given I'm at this point. So for example, if I'm in the center of the circle and I have a small square, the probability of going into that square is 1, because I'm in the center of the circle and it's a small square. And the probability of going outside of that small square is completely 0 because of the mechanism I'm using. So this gives me a probability distribution given my current state, given where I am right now. And this is the object we have to study to ensure that we are following a correct path, a correct process. So now the key to LCMC is to construct good kernels, this is called a kernel, so that we can obtain nice samples from G. What is a good kernel? In the circle example, the size and shape of the box will tell me a good or bad kernel. If my box is very tiny, I will move very slowly in my circle. If my box is too large, I will keep rejecting it. Right? So there is a trade-off, I have to choose that. And in the normal example also, do I want to choose a normal distribution? Do I want to choose what is the variance or the fatness of the distribution that I want, wide decimal? Okay. Maybe I'm low on time, so I'm not going to talk about this part here. What you basically the takeaway is that if you run this Markov chain, you have good properties like stationarity and ergodicity, which tell you as you run the Markov chain, you will converge to the true distribution in some reasonable way. So convergence now needs to be measured in some way. It's one way to measure it is by the difference between the distributions of your Markov chain at a certain time t and your target distribution, which is G. Okay, and one way to measure this is through total variation distance, but if you've had advanced courses in probability, there's Wasser-Stein distance and so on. Okay, so I'll just give you a quick visualization. What I'm doing here is I'm starting from -1 and I'm showing you what various Markov chains in principle do. So I start at 1 as my starting value, and if I run the first step of the Markov chain, I will get most values close to 1 and then some values around here. This is the representation of one step of the Markov chain. If I run the Markov chain for 2-3 steps, I reach to a distribution like that. And if I keep running the Markov chain for a long time, very quickly it starts looking like my target distribution. This is a demonstration of convergence to the target distribution. Okay, convergence measured in some way. Okay. Alright, so I'll just end on where is the research in this area. Okay, just a final thought. So when we ask questions like, do we have a law of large numbers, do we have central limit theorems and things like that, there's a lot of math here. When I say math, I mean probability theoretic math. there's a lot of work we need to do in this research in this area, given you have a completely new G that कोई आपके ऑफिस में आगे छोड़ गया, right? And now you need to construct Markov chains that actually target that G, right? That's the target distribution. That requires a lot of math also, but a lot of coding as well, because you have to eventually code these things. Quantifying the error in the estimates that I finally get, that how variable are these objects, that requires a lot of statistical knowledge, and that was part of my dissertation now many years ago. I also now what I work on is finding new ways to draw these samples. हम square ले सकते हैं, हम ellipse ले सकते हैं as my proposal mechanism, हम एक oblong shape ले सकते हैं. In that example, I can also in other examples I might have to come up with basically different types of G, for example. Right? That requires a lot of math, a lot of statistics, geometry knowledge, calculus knowledge, but also wicked amount of coding as well. And then you have a lot of theoretical guarantees. आप किसी को जाके दे रहे हैं computer vision में पूरा algorithm और आप बोल रहे हैं शायद चलेगा देख लीजिए. That doesn't work, right? They need some theoretical guarantees, and that also requires a lot of math and statistics, a lot of knowledge. Okay. I'm going to end here. There's many applications. There's some cool new applications in LLMs and like Netflix movie recommendation systems and things like that use XCMC all the time. Thank you so much for listening to me. If folks are interested in pursuing a PhD and you have some coding skills, you like mathematics and also want real life relevance, we have a lot of students in our PhD students in our department who actually come with a math background as well, pursuing a PhD instance. So feel free to let me know. In traffic, yeah, actually, so I have a colleague in IIT KANPUR who's a civil engineer who works on traffic problems, and he uses Monte Carlo methods all the time. Yeah, so the models for these need to be built together with some sort of a story. There's a story that typically tells you how traffic flows, because this is a generally learned area, how traffic flows on average. Then you observe some data about real traffic that you observed that was flowing. Now to actually convert the model and the data and combine it together, eventually what you get into is you have these integrals that you have to basically integrate over all possible flow paths. That's exactly where this is used in traffic. I will not, so I will be very careful and say it's not used in analyzing it. So something to understand is that Monte Carlo integration